accidentally ended the video for this section before I wanted to, so it's easier for me just to redo it again than to try to edit it. But in section 4.2, we're going to talk about linear models. And when we discuss linear models, we're going to discuss models that we can use this function to define. That's a function of some value. Here we're just saying a function of t equals mt plus b, where m is a constant rate of change, t is our independent variable, and b is our y-intercept. Now notice when we're discussing functions in this way, when we're modeling stuff where time goes, say, from 0 to time t, that when time is at 0, that's the start of our situation. So where we cross the y-axis here, the y-intercept, that's an initial condition. So that's usually the starting condition for whatever we're modeling. And then this thing continues at a constant slope, or m, so a constant rate of change. Okay, so here's an example of creating a model. A town's population is growing linearly. In 2004 it was 6,200 people. In 2009 it rose to 8,100. Create a model that represents this, a linear model that represents this essentially. So probably one of the first things to do is to think about this in a graphical sense. So imagine what's really going on, and you know, even if you're taking a test, you might want to take the time to sit down and sketch this out. So I put a y-axis here and an x-axis here, and x is my time, and the important numbers are 4 and 9 here. Now on the y scale, I've got 6,000 here to 8,000, so I can account for these large numbers. So I marked out where these point pairs are. So the first point is in 2004 with 6,200 people. Well, I left off the 2000 part, so 200 on both of these. And as long as we keep that in mind, as long as we keep in mind the number we represent is 2000 in something, it's okay to do that. So I have 4, 6,200 as my first point, and my other point, my other piece of data is 9 and 8,100. And as you can see, we can draw a straight line between those with a constant slope. So I can model this with a slope-intercept equation, or function for my line. So this is really a function. Oops, let's get a color we can see. This is really f of x equals y equals mx plus b. And we need to figure out what m is and what b is to complete our model here. So the first step, m, our slope, or our constant rate of change, is modeled this way. M equals y2 minus y1 over x2 minus x1 equals 8,100 minus 6,200 divided by 9 minus 4, which is 1,900 over 5, which is 380. So our function equals 380x plus b. Well, we're still missing this b. So now we have to figure out b. So if I had this thing drawn out, the y-axis, if I started at 0, these would be way up there and there'd be a lot of empty space over here. And where we cross the y-axis, way down here someplace, that's what b is, and that's what we have to figure out. So we have to figure out what, for this model, what would be the initial condition. So we need to figure out what b is. How might we go about this? Well, we do have two pieces of information that came in the problem, namely, oops, this isn't working. Okay, now I got it raised up. Namely that in 2004 we had 6,200 people, and in 2009 we had 8,100 people. So notice, by definition, these 2 points are means these 2 points should satisfy our function. So if these 2 points satisfy our function, then either of these points can be used to figure out what b is, and we should get the same answer either way. So let's choose one of these points. So this is something equals 380 plus b. So we'll stick in 9 for our x value and 8100 for our y value. So I chose this point. Run through this calculation. I get, what is this, 8100 minus 380 times 9, and this all equals b, which equals, equals 4680. So our model then is, let's see if we can get this to go down a little. F of x equals 380 times x plus 4680. Well, before we go on, let's check this. And we'll use the other point to check it for 6200. And after I do the math, 6200 does equal 6200. So that check at least worked out. So what does this mean? This means our model here for our town's population data is here. And at time 0, this model started at 4680. That means that whenever they were taking the initial information, that was the first data point, supposedly. Or somewhere around there. It's probably close. Sometimes while working with linear systems, we can set up a diagram to help us figure out what's happening, as opposed to a Cartesian plot. For example, Anna and Emmanuel start together and they start walking. Anna heads due east at 4 miles per hour, while Emmanuel moves south at 3 miles per hour. How long until they are 2 miles apart? Well, their rate of change of their movement is linear here. So we're going to be able to set up a linear problem. First off, let's think about Anna. She's moving east. So typically we consider that to the right. So this is Anna. And she's moving at 4 miles per hour. So to figure out how far Anna moves in a certain amount of time, we could just multiply this 4 miles per hour times the time she moves, times t. So, for example, if she travels for 2 hours, 2 miles, so 4 miles per hour times 2 hours. I'm just going to put over 1 just so you see here. Notice the h's cancel out, and we have 8 miles left. That's how far she travels in 2 hours. So that's why it's a good idea to use t here. So t is a variable. This is a constant rate of change. On the other hand, Emmanuel is heading south. Not quite as fast, but notice this is 90 degrees from each other, and he's heading at 3 miles per hour. The same idea holds. If she travels 8 miles in 2 hours, then he travels 3 times 2 is 6 miles in 2 hours. So we can see how these are related. Now, since this is a right triangle, we can use Pythagorean's theorem to figure out the distance between these two and get this. And we know, based on our problem, what we're trying to solve, we want to figure out what time happens when this distance is 2 miles. So he's traveled this way, she's traveled that way. When she is here and he is here, they are exactly 2 miles apart. We've got ourselves a nice right triangle. We can just use the Pythagorean theorem to solve this problem. I'll let you go ahead and solve this. If you have trouble with this one, this is example 2. Example 2 in your book. It explains exactly how to do it. Okay, another thing we might end up doing when we're working with linear equations is we might use systems of equations to solve for pieces of information. For example, 2 or more linear equations, so 2 lines. We might look at those 2 lines. We might look at situations where when does one line start producing a value for f of x larger than another line, or where are those 2, at what time or what period do those 2 lines become equal. So again here, plotting information is a really useful means of getting a quick intuitive idea what's going on. So let's jump into an example problem. Okay, say Jamal is choosing trucking rental companies, and the first charge is $20 for a truck plus 59 cents per mile, while the second, he's comparing these, while the second charge is $16 to rent a truck plus 63 cents per mile. So one of them charges less to rent the truck but more per mile than the other. So let's figure out how many miles of use Jamal can make out of these trucks where they'll both end up costing him the same amount. This will help him make a decision. So we can write linear equations here for this information. For the first one, let's call it f of x. F of x equals 0.59 times x, I guess. I was going to put p here, but times x, since I'm using x in my function, times x miles, but the truck also costs $20. And the second one, we'll call it g of x, equals 0.63x, and the truck cost has an initial charge of $16. Well, as you can see, these are 2 lines each, and the first one, should have done these in different colors. Let me go back and color them. Okay, so now I have an orange and a green line. So for our green line, our initial condition here is at 0, when x is 0. If you don't use the truck at all, don't drive the truck at all, but you rent it for a day, it costs you 20 bucks. But it has a cost of 59, so that's going to be some slope, positive slope, which means that as the number of miles, so let's make x here equal to miles, as the number of miles of use increases, so linearly does the cost for this truck. Okay? Now the second one has an initial condition a little lower, so it's over here at 16, and it has a slope that is higher. So the question I was asking is, what are the number of miles when these prices are equal? They're equal when they cross each other. They'll have the same f of x value. So this is called a system of equations. Well, these are equal when the g of x function equals the f of x function. So if I put the equations here, 0.63x plus 16 equals 0.59x plus 20, and then I do the algebra, I can solve for x, and x equals 100. So this x is 100, and now you can make a decision. You can see that if you're going to use more than 100 miles, that the green, or company A, is the better choice because it'll leave you with less cost. And if you're going less than 100 miles, then the orange, or the second company, is the way to go.